Atoms in Motion 101 Introduction. This 2-year physics course is presented as if you, the reader, are going to become a physicist. Of course, that may not actually be your goal, but every teacher tends to assume that their students will enter their field. If you were to become a physicist, you would have a tremendous amount to study, more than 200 years of rapidly expanding knowledge. In fact, there is so much information that it cannot realistically be mastered in 4 years. Most physicists must continue their education in graduate school. Despite this enormous body of knowledge, it is possible to summarize much of it using a relatively small number of fundamental laws. These laws condense a vast amount of scientific results into simpler principles. However, the ideas behind these laws can be difficult to understand. Because of this, it would be unfair to start studying physics without first having a general map of how different scientific ideas relate to one another. For this reason, the first few chapters will introduce the relationship between physics and other sciences, how different sciences connect with each other, and what science itself means. This overview will help develop a general understanding before studying detailed topics. You might ask why physics cannot simply be taught by stating all the basic laws first, similar to Euclidean geometry, where we begin with axioms and derive everything else from them. Unfortunately, physics cannot be taught that way for 2 main reasons. First, we do not yet know all the fundamental laws of nature. Science continues to expand, and there is still a large frontier of unknown knowledge. Second, the most accurate statements of physical laws involve unfamiliar ideas and advanced mathematics. A student needs considerable preparation just to understand the concepts involved. Therefore, physics must be learned step by step. Each idea we learn about nature is only an approximation of the full truth, or at least the best truth we currently know. Scientific knowledge is always evolving. What we believe today may later be corrected or improved as new discoveries are made. The basic principle of science can be summarized simply: experiment is the ultimate test of all knowledge. Experiment determines whether a scientific idea is correct or not. But where do scientific laws come from? Experiments provide clues and hints, but imagination is also essential. Scientists must use creativity to form general theories based on experimental evidence. These theories are then tested again through experiments to see if they are correct. Because this process requires different skills, physics often involves 2 types of scientists: theoretical physicists, who develop mathematical theories and propose new laws; experimental physicists, who perform experiments to test and verify those ideas. Scientific laws are often approximate. Early laws may later turn out to be slightly incorrect. For example, scientists once believed that mass never changes. According to the original law, the mass of an object remained constant regardless of its motion. Later discoveries showed that this is not entirely true. As objects move at speeds close to the speed of light, their mass increases slightly. However, at everyday speeds the change is extremely small. For example, if an object moves slower than about 100 miles per second, the change in mass is less than 1 part in a million. For practical purposes, the original law works well in most everyday situations. But at extremely high speeds, it becomes inaccurate. Even though the change is small, it forced scientists to rethink their understanding of the universe. New ideas such as Einstein's theory of relativity introduced concepts like 4-dimensional space, time. This creates an important teaching challenge. Should we start with the most accurate but complex theory, or begin with the simpler approximation that is easier to understand? The complex theory is more exciting and accurate, but the simpler one is easier to learn first. In physics education, both approaches are sometimes used. At each stage, we learn what is currently known, how accurate it is, and how it might change with future discoveries. With this perspective in mind, we can now begin building a general picture of how science, and especially physics, explains the world. 120. Matter is made of atoms. Imagine that all scientific knowledge were suddenly destroyed and only one sentence could be passed to future generations. Which sentence would contain the greatest amount of information? The most valuable statement might be this: all things are made of atoms, tiny particles that are constantly moving. They attract each other at moderate distances, but repel each other when pushed too closely together. This simple statement contains an enormous amount of information about how the world works. To understand its significance, imagine a small drop of water about a quarter inch across. If we look at it with our eyes, it appears smooth and continuous. Even with a powerful optical microscope magnifying about 2,000 times, the drop would appear about 40 feet wide, yet it would still look mostly smooth. At this scale, we might notice tiny organisms, such as paramecia, swimming through the water. Studying those organisms belongs to biology. But suppose we magnify the water again by another 2,000 times. Now the drop would appear about 15 miles wide, and we would begin to see a crowded, constantly moving collection of particles. If we magnified it even further, about 1 billion times, we would see individual molecules. Each water molecule consists of one oxygen atom and two hydrogen atoms joined together. These particles are not stationary. They are constantly moving, vibrating, and colliding with one another. They also attract each other slightly, which helps keep the water together. Atoms are extremely small, about 1 to 2 angstroms in radius A, and angstrom equals 100 A, 810 A, 810 I 8 centimeters. To imagine their size, consider this comparison. If an apple were magnified to the size of the Earth, the atoms in the apple would be about the size of the original apple. Atomic motion and temperature. Inside a drop of water, molecules are constantly moving and vibrating. This motion is what we experience as heat. When temperature increases, the motion of molecules increases. As they move faster, the average distance between them becomes slightly larger. If the temperature becomes high enough, the attractive forces between molecules are no longer strong enough to hold them together. The molecules separate and become steam or water vapor. In steam, molecules are much farther apart and move freely. They collide with the walls of any container holding them. These collisions create pressure. For example, imagine many tennis balls bouncing randomly inside a box. Every time they hit the walls, they exert force. Gas molecules behave in a similar way. If we double the number of molecules in the container while keeping the temperature constant, the number of collisions doubles. As a result, the pressure also doubles. If we increase the temperature instead, the molecules move faster. They collide with the walls more often and with greater force, which also increases pressure. These simple ideas form the basis of the atomic theory of gases. Compression and temperature. Now imagine pushing the piston of a gas container inward. As the piston compresses the gas, molecules collide with it and bounce back with greater speed. Because of these faster collisions, the molecules gain energy. As a result, the temperature of the gas increases. Conversely, if the gas expands slowly, the molecules lose energy and the temperature decreases. Solids, liquids, and ice. When we lower the temperature of water, molecular motion decreases. Eventually, the molecules become locked into a regular structure called a crystal lattice. This solid form is known as ice. In a solid, atoms occupy specific positions in an ordered pattern. The arrangement of atoms on one side of a crystal determines the arrangement throughout the entire structure. However, even in solids, atoms are not completely motionless. They continue to vibrate in place. As temperature increases, the vibrations become stronger until the crystal structure breaks apart and the substance melts. Interestingly, water behaves differently from most substances. The crystal structure of ice contains open spaces, so when ice melts, the molecules move closer together. This is why ice is less dense than liquid water and floats. Atomic motion at absolute zero. As temperature approaches absolute zero, atomic motion decreases to its minimum possible level. However, according to quantum physics, atoms never become completely motionless. Most substances freeze at extremely low temperatures, but helium is unusual. Even at absolute zero, helium atoms still move enough to prevent freezing unless very high pressure is applied. The big idea, the atomic hypothesis, tells us that everything in the universe is made of atoms. From the movement of water and the formation of ice to the behavior of gases and chemical reactions. Every physical phenomenon can be understood in terms of atoms interacting according to the laws of physics. Even living organisms are ultimately complex arrangements of atoms. The incredible complexity of life arises not from something mystical, but from the astonishing ways in which atoms can organize themselves. In this sense, a human being is not merely a pile of atoms, but a highly organized and incredibly complex system of atoms, capable of thought, movement, and consciousness.